Hello, this video includes information on molarities, percent by mass volume, and percent by volume calculations.
Solutions are a homogeneous mixture of two or more substances, okay? So we wouldn't be able to see the individual components in the mixture. They're uniformly distributed. And there are two components that we talk about when we deal with solutions. The solvent is usually the substance that's in the larger quantity, and it's the substance that's going to dissolve the solute. And the solute is the substance that's usually in the smaller quantity, and there can be many solutes. Sometimes there's only one solute, but sometimes there can be more than one solute. So as an example, if we were to take this orange solid here, which is called potassium dichromate, and dissolve it into water, we're going to make a solution. The water is the solvent, and the potassium dichromate is the solute. And when we look at this solution, we can no longer differentiate the water from the potassium dichromate. Now, when we talk about solutions, their composition varies. Okay, we can have very diluted solutions, meaning there isn't a whole lot of solute relative to the solution. Or we could have very concentrated solutions, meaning there's a lot of solute relative to our solution. And there are different ways that we can talk about the composition of mixtures, of solutions. We're going to look at molarity first. And you should notice that it kind of has the word mole in it. So when we talk about molarity, the symbol is a capital M. So oftentimes we don't write the whole word out, we just use a capital M. And it's the number of moles of solute per liter of solution. So we could write it as an equation: molarity equals our moles of solute per liter of solution. So maybe the easier type of question we could see is, all right, we're going to take some salt and we're going to dissolve it into water. And we want to calculate what the molarity is. But to calculate the molarity, the first thing you should do is write down what the equation is so you know what you need to figure out. So we need the moles of the solute. It gives us grams. We're going to have to convert grams to moles before we can plug it in here. And we're going to need the liters of the solution. We're given the milliliters, so we need to convert that to liters, and there are 1,000 milliliters per liter. So if we've got 3.40 grams of sodium chloride in 125 milliliters of solution, we'll just do some dimensional analysis. We're going to convert grams of sodium chloride to moles. And the periodic table tells us there's 58.44 grams for every mole. So we've converted the numerator into the units we're looking for. The denominator is milliliters, but we need to get it to liters, and there's 10 to the third milliliters per liter. That'll give us moles per liter for units at the end. So we have the problem all set up. We're just going to take 3.40 divided by 125, and then divide it by 58.44, and then multiply it by 1,000. And that'll give us our numerical answer. Now there's 3 digits here and 3 digits here, so we're going to round this to 3 digits, so 0.465 moles per liter. But oftentimes, instead of writing moles per liter, we just use a capital M. And this capital M stands for moles per liter. We have to know that's what it means. But we would say it's a 0.465 molar solution. And it's a way of talking about the concentration of a solution. So let's say we have a problem like this. Let's say we have kind of the opposite of what we did before. How many grams of calcium chloride would you need to make 250 milliliters of 0.100 molar solution? All right, well, we're looking at molarity. What we have to remember is that really molarity is a unit conversion. It tells us how many moles there are per liter. And that's what we're going to use to get to grams of calcium chloride. Now, what are we given? Well, we're given the volume. So we'd start with the 250 milliliters. We'd have to convert milliliters to liters. Then we can use this conversion factor, our molarity, to convert to moles of calcium chloride. And then we'd have to convert to grams of calcium chloride. That's our thought process. Now let's look at the problem worked out. So if we have 250 milliliters of solution, this is what we're given. Okay, notice there's a decimal here that tells us there's 3 digits. The first thing we're going to do is we're going to convert that volume to liters. Once we have the volume in liters, we can use our molarity as our conversion factor. We're going to convert from liters to moles. Now, once we're at moles of calcium chloride, we can go from moles to grams. Now, where does this 110.98 come from? It comes off the periodic table. Okay, it's the molar mass for calcium chloride. Okay, calcium times 1 plus chlorine times 2. Okay, just comes off the periodic table. So if we were to mass out 2.77 grams of calcium chloride and put it into 250 milliliters of total solution, the molarity of that solution would be 0.100 moles per liter, the concentration. So kind of the third variable, okay, is what if we wanted to calculate the volume? Okay, so it says how many milliliters of an aqueous solution of 0.235 molar silver fluoride is needed to obtain 9.72 grams of silver fluoride. And now again, we need to remember what this 0.235 molar really means. It's really the conversion factor that tells us there's 0.235 moles per liter in this solution. So from there, we're given 9.72 grams of silver chloride. Well, we can convert that to moles. If we convert that to moles, we can use our molarity as our conversion factor to cancel out moles and go to liters. And then the question wants milliliters, so we'd have to do a conversion on the tail end of the problem. So we're given 9.72 grams of silver fluoride. Now, silver's a +1, fluoride's a -1. Okay, you were given the name of the compound. You need the formula to do the problem. Okay, now we're going to convert from grams to moles. And this 126.88 grams comes from the periodic table when we look up silver fluoride. Silver times 1 plus fluorine times 1 gives us 126.88. So we're going to convert from grams to moles. Then we're going to convert from moles to liters using the molarity as a conversion factor. And remember that 0.235 molar solution means we've got 0.235 moles per liter. We want to cancel out the moles, so 0.235 moles in every liter of solution. And then we want to go from liters to milliliters, and we know there are 1,000 milliliters in a liter. So we would need 326 milliliters of total solution in order to give us a concentration of 0.235. So when we look at molarity, molarity equals moles per liter. Either we're given the information to figure out the moles in the liters, we can calculate the molarity, or we're given the molarity and we can figure out the moles so we can calculate the volume, or we're given the molarity and the volume and we can calculate the moles. So out of that 3 variable equation, we're going to have 2 out of 3 and we're going to figure out the third. So let's look at another problem. We're going to add a step onto this problem. It says a solution is prepared by placing 2.50 moles of calcium chloride in a volumetric flask. And we'll look at that in a couple of minutes. It's just a flask that's used to measure volumes for solutions. And filling it to the 1 liter mark with water. The first thing we want to do is calculate the molarity of the solution. Okay, so the molarity of the solution, molarity equals moles per liter. So here's our moles for the calcium chloride. Here's the volume for the calcium chloride. So the first part's pretty straightforward. The molarity of the calcium chloride is 2.50 moles per liter. So we get 2.50 for the molarity. But the second part of the problem says calculate the molarity of each ion present in the solution. When calcium chloride is added to water, what it actually does is it breaks up into its ions. And for every 1 mole of calcium chloride that dissolves, we're going to get a mole of calcium ions, and we're going to get 2 moles of chloride ions. So if we were to look at the calcium ion concentration, it's going to be the same as the calcium chloride originally because it's a 1-to-1 ratio. But if we were to look at the chloride ion concentration, the molarity for the chloride ion, it's a 1-to-2 ratio. So the chloride ion would be twice the calcium ion concentration. Okay? Questions so far? Everybody okay? And again, if you have a question, just speak up or put your hand up. Hand up actually has been working really well. Or just put it in the chat. All right. So let's look at this one. This is actually called a hydrated compound. So it says how many moles of, we would call this cobalt chloride dihydrate. For every 1 cobalt chloride, there are 2 water molecules linked to it. This dot means they're linked together chemically. It's not really a multiply sign. So when we go to figure out the molar mass for this hydrate, we would take cobalt times 1 plus chlorine times 2 plus hydrogen times 4, 2 times 2, plus oxygen times 2. This 2 kind of gets distributed into the water if we've got 2 water molecules. So we would just add that up and that would give us the molar mass for our hydrate. So we want to find out how many grams. Okay, we're given the volume and we're given the molarity. And again, that molarity is going to be the conversion factor between volume and moles of solute. So we start with our volume. We're going to need to convert it from milliliters to liters. We're going to use our molarity as our conversion factor to get to moles. And then we're going to use the molar mass to get to grams. I'll give you a minute. Let's see if you can work that out, and then we'll look at the answer. Okay, so we've got 0.5, just didn't show the conversion here. So 0.500 liters. We're going to use our molarity to convert from liters to moles. And we're going to use the molar mass to convert from moles to grams. And again, where does this 165.87 comes from? We're going to use our periodic table. 1 times cobalt plus 2 times chlorine plus 4 times hydrogen plus 1 times oxygen. And that gives us our molar mass. And then we take 0.500, multiply it by 0.121, multiply it by 165.87, and that's going to tell us we need 10.0 grams of cobalt chloride dihydrate in 500 milliliters of total solution to give us a concentration of 0.121 molar. All right, so I just wanted to point one little thing out about making solutions, kind of just to clarify, because it's a big misconception. So let's say that we're making the solution we just calculated. So we've got, our balance here. Okay, we mass out the 10.0 grams of the cobalt chloride. We this is what a volumetric flask is. Okay, it's used to make solutions. It's got an etched line in its neck, which is exactly 500.0 milliliters. So we carefully take that cobalt to chloride dihydrate, we put it into our volumetric flask, we add our solvent, the solvent's ethanol, it doesn't matter in the calculation. We dissolve it, okay, shake it around, make sure all the solutes dissolved, and then we keep adding the solvent until it gets to that etched mark. The volume of the total solution is 500 milliliters. Now, here's kind of the misconception, okay? If we were to look at this as an example, okay? It's a different solution, but it doesn't really matter. So we've got our balance, okay? We massed out 90 grams of, this is ammonium dichromate, not that it necessarily matters, but we put it into our volumetric flask. Now, the volumetric flask is a 250 milliliter volumetric flask, okay? And we're making 250 milliliters of total solution. What that doesn't mean is we're adding 250 milliliters of water to the volumetric flask. Because if we were to add the water from the graduated cylinder into the volumetric flask until we get to that etched mark, we actually have water left over. And the reason for that is the solute that's in this solution is actually occupying some of the volume. So we're not adding 250 milliliters of water to our 90 grams of solute. We're taking the 90 grams of solute and adding water until the total volume is 250 milliliters. And that's a big misconception about making solutions with volumetric flasks and molarities. It's the volume of the solution, not the volume of the solvent that we're using in the solution. Okay, and I kind of wanted to show that and kind of clarify that because it's a pretty big misconception. All right, so now let's talk about dilutions. Okay, and essentially dilutions mean we're watering down a solution. And when we water down the solution, we don't change the amount of solute that's in the solution. We add more solvent. So the ratio of the solute to the solution goes down as we dilute it. So again, just kind of a little, picture diagram here. So we have our original solution, okay? It's called our stock solution. That has a known concentration. And what we would do is we would pipette out a particular volume of that solution, and we'd add it to an empty volumetric flask. And then we would add the solvent to get to the etched mark in that new volumetric flask, and we would dilute that solution. Okay, we dilute the solution by adding solvent to water down the original solution. So we're not going to be changing the amount of solute, but we're going to change the total volume of the solution when we go through a dilution. So let's say that our stock solution is a 0.100 molar solution. And we draw up 10.0 milliliters of that stock solution. And we put it into this volumetric flask. And we dilute it to the 1 liter mark. What would the new concentration be? Well, that's a dilution problem. So when we go to calculate dilution problems, what we're always going to have is an initial volume and molarity. So in this case, we had 10 milliliters of 0.1 molar solution. And we're going to dilute it to a new volume. What's the molarity going to be? Now, the key to dilution problems is that the total number of moles of solute you had in the original solution is the same as the number of moles of solute you have in the diluted solution. We're not changing the amount of solute. But what we are doing is we're changing the volume of the solution, which in turn changes the molarity of the solution. So our equation for dilution problems is M1 times V1 equals M2 times V2, okay? The M's stand for molarities. The V's stand for volumes. The 1's are for the original concentrated solution, and the 2's stand for the diluted solution. So in this particular question, we're trying to calculate M2. So to calculate M2, we would just take this dilution equation and solve it for M2. We have to divide both sides by V2 to do that. So M1 times V1 divided by V2 would give us our new molarity. So we take the molarity times the volume of the original solution, divide it by the volume of the diluted solution, and we're going to see that that molarity has gone down. Okay, we're watering it down. We're diluting it by adding solvent to a given amount of concentrated solution. It's a fairly easy calculation. All right, so here's another question. See if you can work this one out on your own. It says a chemist wants to prepare 0.25 molar HCl. Remember, HCl is an acid because it's got hydrogen as its positive ion. Okay, it doesn't have oxygen in it, so this would be hydrochloric acid. Okay, so 0.25 molar hydrochloric acid. Okay, the commercial hydrochloric acid, the way that it's shipped to laboratories, is 12.4 molar. And rarely do we use such concentrated hydrochloric acid in a lab. So we're going to want to dilute the 12.4 molar down to 0.25 molar. Okay, how many milliliters of this 12.4 molar hydrochloric acid would we need to make 1.50 liters of 0.25 molar? Okay, so it's a dilution problem. Think about what the equation is that goes along with dilution problems. Out of the 4 variables, you know 3. You're trying to calculate V1 in this particular question. Okay, so whenever we're looking at a dilution problem, it's M1V1 equals M2V2. In this case, we want to find out what the volume of the concentrated solution is. So we're trying to find V1. We're going to have to divide both sides by M1 so that we have our equation, and then we plug in the numbers. We just need to make sure we keep the numbers together. So the 0.25 molar and the 100 or 1.50 liters go together. That's the diluted solution. And then we have the concentration of the concentrated solution in the denominator. So we would need, did it ask for milliliters? It did. So 0.030 liters or 30 milliliters of the concentrated solution. And then we dilute it to 1.50 liters and it would go down to 0.25 molar. All right, so we have another one. In the laboratory, you dilute 5.32 milliliters of concentrated 12 molar hydriodic acid, okay, that would be HI, a hydriodic acid, to a total volume of 75 milliliters. What's the concentration of the diluted solution? Okay, so you've got an M1V1 equals M2V2. It's a dilution problem. Okay, out of the 4 variables, think about the 3 that you know. Calculate the missing variable. All right, so we've got M1V1 equals M2V2. When you're dealing with dilutions, here's your equation. This time we want to calculate the molarity of the diluted solution, so we want to calculate M2. So it equals M1 times V1 over V2. Okay, the molarity and the concentrate and the volume of the concentrated solution go on the top. The volume of the diluted solution goes on the bottom. So when we dilute that solution, the new molarity will be 0.851. All right. So there are other ways that we can talk about the composition of a mixture, okay, or the concentration of a mixture. We can use molarity, okay, which is what we were just working on. We could also talk about it in terms of percentages. And there are 3 different ways that we can deal with percentages. We can deal with it in terms of masses, okay? The mass of whatever we're talking about, the component, divided by the mass of the solution times 100. Okay, like if we had a salt water solution and we knew the mass of the salt and we knew the mass of the solution, we could figure out what the mass percent is. Okay, we could talk about it in terms of volumes, the volume percentage. Okay, the volume of the component we're looking at over the total volume times 100. So let's say that we've got a solution of alcohol and water, and we've got 10 milliliters of alcohol in 100 milliliters of solution. Okay, we would take the 10 milliliters divided by the 100 milliliters times 100. Or we could do it in terms of mass volume percentage, the mass of the component, okay, the part of the solution that we're looking at, divided by, 100 milliliters of solution times 100 would give us the mass volume percentage. So let's look at a couple of questions. Okay, it says an aqueous solution of ammonium acetate contains 2.35 grams of ammonium acetate and 17.5 grams of water. Calculate the percentage by mass of the ammonium acetate in the solution. So we need to know the mass of the component, in this case, the ammonium acetate, and we need to know the mass of the solution. Now, this is not the mass of the solution, the 17.5 grams. This is the mass of the water. So if we wanted to figure out the percent of ammonium acetate by mass, it would be the mass of the ammonium acetate, okay, the 2.35 grams, divided by the total mass of the solution. And we know that because of the law of conservation of mass, we just have to add the solute and the solvent together, and that'll give us the mass of the solution. So we're taking the component we're looking at, dividing it by the total, and multiplying it by 100. So this particular solution is 11.8% by mass. So let's say we want to find out how many grams of this ammonium acetate are in 198 grams of solution if it's 11.9% by weight or by mass. So this time we know the percent, we know the solution, we want to figure out the solute. It's the same kind of problem. It's just a different variable. So we've got 198 grams of solution. And the percent tells us it's 11.9 grams in 100 grams of solution. So this is an easy way for us to write that 11.9%. 11.9% really means 11.9 grams of solute per 100 grams of solution. So we can use this mass percent as a conversion factor. We're going to convert from grams of solution to grams of solute. So this 198 grams of solution would have 23.6 grams of ammonium acetate in it. All right, so let's look at one that's a volume percent. Okay, we've got ethanol in a solution. Okay, so we've got 38 milliliters of ethanol. That's our solute. And we have 100 milliliters of toluene. That's our solvent. And it doesn't matter that we don't know what toluene is. It's just the other component in the solution. So if we want to figure out the volume percent, we would need to know the volume of the component we're looking at and the total volume of the solution. And we're going to assume for these kinds of problems that volume is additive. That's not always the case. And we're going to look at some problems where that will not be an assumption that we're going to make. But for this problem, we've got 38 grams of ethanol. And we've got 100 or milliliters, 38 milliliters of ethanol. And we've got 100 milliliters of toluene and 38 milliliters of ethanol. It actually doesn't say times 100. It should say times 100 here. And that tells us it's a 28% by volume ethanol in the solution. All right, now we're going to look at a problem that's a little bit more complicated. Okay, it tells us that we have an ethanol solution and it's 12% ethanol by volume. Again, what does that mean? It means there are 12 milliliters of ethanol in every 100 milliliters of total solution. That's what this number means. And it tells us that the density of ethanol is 0.789 grams per milliliter. We want to calculate how many moles of ethanol are in 750 milliliters of this solution. Okay, and it happens to be a wine solution that's 12% ethanol. Ethanol is drinking alcohol. Okay. So what we would do is we would start with the 750 milliliters. We're going to be using the percent by volume as a conversion factor, knowing that this means there's 12 milliliters of ethanol for every 100 milliliters of wine. And we're going to be using the density as a conversion factor, knowing that 0.789 is how many grams there are per milliliter. So the starting point is 750 milliliters. Okay, so 750 milliliters. We can convert that from milliliters of wine to milliliters of ethanol because it gives us the percent by volume. So 12 milliliters of ethanol in 100 milliliters of wine. This will do our conversion from wine to ethanol. Then we're going to use our density to go from milliliters of ethanol to grams of ethanol because that's what the density tells us, how many grams there are per milliliter. So now we're at grams of ethanol, but the question wanted moles of ethanol. So we're going to convert from grams of ethanol to moles. This number comes off the periodic table. Here's the formula for ethanol. It would be carbon times 1 plus hydrogen times 3 plus carbon times 1 plus hydrogen times 2 plus oxygen times 1 plus hydrogen times 1. All of that added together off the periodic table gives us that 46.06. So now that we have the problem set up with our conversion factors, again, this comes from the percent by volume, this comes from the density, this comes from the molar mass off the periodic table, we would take 750 times 12 divided by 100 times 0.789 divided by 46.06. And we get 1.5 moles of ethanol in 75 milliliters of solution to give us a 12% by volume composition for our solution. All right, let's look at one more. Okay, actually covered up. Give me a second. We've got 1.4% by mass phenol in water to make a throat spray. Okay, it tells us that the solution is 0.9956 grams per milliliter for its density. And we want to calculate its molarity. We need to remember what molarity is. It's moles per liter. Okay. So we would start with that. Somehow we have to figure out moles per liter. And then we do our conversion. So the percentage tells us that there's 1.40 grams of phenol in every 100 grams of throat spray. We can look up phenol on the periodic table, and it's 94.12 grams per mole. So we've got this part, the numerator's all done. And then we're going to look at the grams of solution, and we can convert from grams of solution to milliliters of solution using the density as a conversion factor. That'll give us moles per milliliter. We want moles per liter, and there are 1,000 milliliters per liter. So 1.40 divided by 100 divided by 94.12 times 0.9956 times 1,000. And the molarity of the solution would be 0.148 moles per liter, or 0.148 M, or we'd say it's a 0.148 molar solution.